Всем привет! И мы начинаем сегодняшний наш meetup. Здесь со мной сегодня Денис. И у нас есть для вас небольшой сюрприз. У нас есть еще один спикер. Это Рана Штейнберг, Golang Developer Expert. По-моему, из Google, но я могу ошибаться. И еще одно небольшое объявление, поскольку получилось так, что наш meetup сегодня международный, мы его решили проводить на английском языке. Не бойтесь, если вдруг у вас появятся вопросы, пишите их в чатике на русском, мы будем их переводить и задавать в реал-тайме нашим спикерам. Также обратите внимание, что у вас будет возможность подключиться к нам в стрим в конце каждого из докладов. Мы будем приглашать вас по ссылочке, выводя в баннер, кидая ссылочку в чатик. Не стесняйтесь. И еще одна опция, которую мы сегодня придумали для вас. Вы можете пообщаться с нашими докладчиками после их презентации в Zoom-канале. Ссылочку также скинем в чатик на YouTube. Всем спасибо, Денис.
Yeah, hello and welcome for everyone. For those who don't speak English, I will just duplicate what Igor just said. So, yeah, welcome for our Go Online Meetup. Today we will have a surprise speaker, Rana. She will have the last talk today. Also, yeah, we will have 3 talks. In case you would like to ask a question personally with your webcam opened, you can just post your comment here and we will invite you. But if you don't like to ask it personally, you can just, in the end of a conference, we will have a Zoom meeting where all questions, or most of them, will be answered. I guess that's it about agenda. And I would like to welcome our first speaker, Artem Navoiev.
Hello, Artem. Artem, I guess.
Yeah, hello guys.
Do you
hear me?
Yeah, we hear you well. One of our experienced expert today. Artem, could you please say a couple words about you and your presentation?
Yeah, hello everyone again. So today I have an option, speak Russian or speak English. So it's basically up to audience. So if someone doesn't understand Russian, definitely it can be in English. So I will wait for some comments in YouTube, on YouTube or other channels. So feel free to speak what language you prefer. Actually, about my presentation and me. So then I'm going to talk about building Kubernetes operator. Also, you all know about Kubernetes. Operator is pretty cool stuff. I will explain how to start doing operatings and what problem can be solved on some particular example. About me, so my main achievement is Go Kyiv Meetup organizer. It's Go user group about 3 or 4 years old, but we stopped our things because of coronavirus and hope everything will be okay after lockdown ends. Some another information, I worked with Go almost 7 years since version 1.3, actually between 1.2 and 1.3. Work on distributed systems and contributed to Azure Cloud, so base called SimpleWare and joined there, and contribution to open source project. It's VictoriaMetrics time series database, which actually.
Okay, I think we shall start. I wish you luck and yeah.
Okay, thank you. Okay, let me keep speaking English. So, about the operators and Kubernetes, the main requirements for that and motivation, you should know Go, at least on the basis. So you should know what Kubernetes is, because you're building stuff for Kubernetes in Kubernetes ecosystem. And the last thing, you you need to have a problem, and you want to manage your resources in Kubernetes cluster, like native Kubernetes application, using all components, but keep and code your own logic, and actually everything will be under your control, but it's still in Kubernetes. So what Kubernetes operator part 10 is? It's extension for the Kubernetes, extension for the Kubernetes API. Actually, it's based on the custom resource and custom resource definitions. And it follows Kubernetes principles. The main idea is the main architecture, which is based on its control loop or recycle loop pattern. More information you will find by using this link. Next, what operator can do? Manage your application lifecycle, handle custom logic of rollout updates, downgrades, performing backup, restore, alerting about your system, gathering and exposing metrics, and do autoscaling. Actually, all infrastructure things you can do by Kubernetes operator. Next slide. Here we talk about two component types in Kubernetes. Right now I'm talking specific to operator and operator needs. So these components we can divide by two params and by two buckets. First is resources. This is actually resources. Config maps, pods, secrets, ingresses, so all the stuff which represent some physical information, some physical component. And controllers are actually, this word says for itself. It's control under these resources. The good example is deployment. Deployment controls the subset of pod. Stateful set, it also controls subset of pod, but in a different manner. And daemon set, it's about the same thing, but here it's not control in particular namespace, it's control on the whole cluster and nodes. The basic resource schema for every resource in Kubernetes, which actually right now it's example of Nginx deployments. And here you can see the basic resource schema. Every resource in Kubernetes has the same schema. And here we can define some four useful types of the schema. First of all, this is type metadata, that's API version and kind. By defining these two params, you say to API server about your resource. They basically probably see API version like V1, V1 alpha, V1 beta, and you see kinds. Some are predefining kinds like pod, stateful set, deployment, ingress, service, or some custom types. That's like Prometheus operator and 3DB operator and some other experience. Another one area is metadata, where you actually store information about your resource, its name, namespace, labels and annotations, and also please point to owner references. Actually, you can put the owner link to your resource, and if owner will be deleted, all child resources will be automatically deleted too. So it's some kind of inheritance and control of child resources. Then it's spec, when you describe your container and also arguments for your application. And the last one, but at least it's pretty useful thing, this status. Status, it's a custom model. Every application defines own status structure. Right now you see condition and array in it. In my example, that will be just a nested object. So you may store whatever you want in the status, and usually it's some state of your application. About customer source and customer source definitions. So customer source is an object that expands Kubernetes API and allow you introduce your own logic. So it's basically your application. If you want to build your application and integrate it in Kubernetes ecosystem with own kind and own logic, that will be customer source. And customer source definition is actually how you describe this object. So for integration to the Kubernetes ecosystem, you need to tell Kubernetes about your source. And customer source definition is actually presentation of this description. So if we speak more easy, that your application is described by customer source definition, your application is customer source, and your operator control application, and actually it's controller and also this resource. And let's actually go to the particular example. Here we'll see the customer source for VictoriaMetrics cluster. I will explain about VictoriaMetrics a bit later, but right now what we see on the screen, we have Meta, like this is version of v1 beta 1, kind customer source. We tell in Kubernetes in what scope and what kind of the resource we have. Then we have, actually next screen will show it. Then we have 4 groups. First of all, name and group. Group need if you have many operators under your domain, so you just define the same group. And name is just particular name of this customer source under your domain, so that will be VM clusters, VictoriaMetrics.com. Another one section, this is names, and you need to describe your kind for the list, single and plural pronunciation of your objects. Actually, this is required for your command line interface. When you write down kubectl get VM clusters, you'll see whole resources by this kind. Next one is scope. Scope is actually pretty cool things. You define the scope of your namespace. Actually, there are only 2 parameters. First of all is namespaces, and second one is cluster. So every word tells about themselves. So namespace, your operators operate, sorry for that, in scope of the namespace. In cluster, you operate resource in scope of whole cluster. And the fourth section here is validation. If you're familiar with the open API format, you can define the validation schema for your customer source and tell that some parameters are required, some are not. And how it works, for example, if you have type replica count and that's int, you say, okay, this is replica count field, it should be int. And when user type tries to type there something another one, for example, word foo, Kubernetes will validate customer source and say, okay, this definition is invalid. Please fix this particular field. So there's some kind of pre-validation for your semantic of customer source. So if we type down in our console kubectl create -f and give this resource as input, we'll register our source in Kubernetes API, and after that we may write down this command. So kubectl get VM clusters, Definitely it says no resource found in default distress because we haven't introduced any resource yet. But the good news here that Kubernetes understands this custom resource, and it registers new API inside its API server. And right now we can perform the regular command for this resource type. It's like for pods, but for VM clusters. And we are going to a bit closer to our operator and actually about operator logic. So we just covered what is resource and how we can describe resource. Another one way of this project is controller, and each controller have the pretty same life cycle. It is actually shown on the screen. So this is loop of events. So first of all, you subscribe on some particular events, and this event will be okay. If something changes with kind of VM cluster, please tell me about that. And actually, this is section of observe. Second one, you have state in your specification file. It's YAML file usually, and you have state in Kubernetes. You usually compare these two states and perform some logic. The basic example here, that's replica set. In replica set, you have a parameter replica. You may define it 3, for example, and it should create 3 pods for you. If user goes and change the definition of replica set and increase value by 1, and that's replicas 4, you have difference between what you have in specification, what you have in Kubernetes cluster, and you perform your action, you need to add 1 new pod. Actually, every Kubernetes operator based on this model, and you need to handle this reconciling loop. Next one. Next one is how we can build our operator. So we definitely don't want to do that from scratch because of huge overhead of Kubernetes API and integration ecosystem to Kubernetes. That's why guys from Red Hat built operator SDK and operator SDK framework. It's like regular framework in every language, but it allows you to build your own operator and define only your logic. All other stuff like receiving the calls, notify Kubernetes about what to do with current loop state, how to handle errors, and what information you want to receive. Everything is handled by framework, so it actually pretty simplify your life. But on the other hand, you have the overhead of vendor lib and all this stuff. So if you want and love to write minimal code, that's definitely your way. But if you want to write fast, easy, and think about the logic, yeah, definitely please use operator SDK. And it supports not only Go, it supports Ansible and Helm. And here we have information about support model and what you can achieve with every type of the framework. So if framework based on the Helm file, you just can send it to Helm file, and it will build operator for you and operator and manage this operator. But inside the cluster, it operator based on Helm can manage only just not many things, just basic installation and handling the schema change on the schema basic change. For example, if you change something in schema, that will be reflected. But custom logic behind this change, this cannot be customized and modified by you. Another two operators types, one is based on Ansible, another one is Go, gives you access to full control for your source. And actually the idea of the operator and what and how you want to build, and when your small operator grows in, it's definitely want to be in phase number 5 and be an autopilot. That means that you don't worry about your application in Kubernetes. It can handle everything without your interruption to the process. So there's auto-scaling, vertical and horizontal, the ascending alerts, metrics, the stuff about its life cycle. It can handle every changes by the user or by other applications. And also it supports updates, rollout updates, graceful rollout updates, and downgrades. We definitely will choose Go operator because we are on the Go Meetup. Next one. So sorry that I jump by step, but I need to gather all information and presented the general idea why I'm talking about operator, what is operator, why it's needed, how it is built, and the problem what we want to solve. And problem right now to solve, we want to build VictoriaMetrics cluster operator. Right now you see the VictoriaMetrics application. We need care about only the big square. This is which consists of 3 parts. First of all, select node, storage node, and insert node. What we should know about these 3 parts? This is 3 different types of applications. Every application is represented by own image and has own meaning and logic. So select just your read data using select. So all user queries go to the select. Select interact with storage node, gather information, and represent it. Insert nodes only cares about the writing data. So application writes the data through the insert node, and the insert node just put it to the storage. And storage is where information is. And let me step back. So VictoriaMetrics is a time series database. So right now you see database cluster version, where 3 types of components. Select and insert a stateless component, and storage as storage, it's stateful component. So if you lost one storage node, we lost the data on this storage node. If you lost some of the VM select or VM inserts, we can afford it because they're stateful. And also that means that we can increase the amount of the stateless component as we want, but with the storage that's a bit complicated, because of if you increase the number of the nodes, that's okay. If you decrease, you lose the data. But with increasing of the number of the nodes, we have problem, which I will describe a little bit further, and that problem we will solve by our Kubernetes operator. Actually, this is part of life cycle. Let me just rephrase it. Storage stateful, select stateless, and the problem is that if you add the one more storage node, you need to perform rollout update of your whole cluster in some efficient way. So another one precondition of that, all insert nodes should know, every insert node should know about whole cluster, because by consistent hashing, it writes data to the particular, to the correct node. Whole select nodes should know about every storage, because every select node reads from all storage nodes. So for example, when we add one new node, for the insert, consistent hashing mechanism should be recalculated and new metric should go to the new node. And for the select, we should start reading from this node, because the end and full representation of the data can be accumulated from whole amount of the nodes. And in that case, we have problem. if you add one new node, okay, new node appear in the cluster, and first of all, we need to start reading for it because if we start writing but not reading, so for example, new node appear, some of start writing on this node, user still reading from the previous subset of the nodes. In that case, user lost the data. So order looks like create new node, start reading for it, and got empty response from the storage node, which is empty because no writing there, and only after that start writing to this new node. Actually, this is a challenge for our Kubernetes operator. And this how our custom resource definition for, this is just resource definition for VictoriaMetrics cluster looks like. As I mentioned before, it has API version under the group, that's 1v beta 1. It has own kind, this is VM cluster. It has example of metadata, that's only name, and you see the specification of each component which I discovered before. So for VM select, for VM insert, and for VM storage. The basic idea, the basic information that we use here is replica count in every. So we start with the 2 replica counts, and after that we'll, based on the logic, based on these fields. So when we have I have file which called VictoriaMetrics cluster.yaml. My Kubernetes cluster knows about custom resource definition, and I type down kubectl create -f and put file with this description as input. In the end, I will have working VictoriaMetrics cluster inside Kubernetes. So it's like you type kubectl create new pod or that was that. And here we are going to use some useful command for generation of our Go project using Kubernetes, using operator framework. First of all, we need to perform all this command. This scope does code generation and YAML generation. First will create your project. The second one will introduce API version and new kind into that project. Next one will generate Go code and introduce, so it just does registration of this API inside Kubernetes, and generate some useful code for initializing and introducing this new definition inside Kubernetes. Fourth one will generate controller. I will tell about a bit later. So basically your code will be split by 2 parts. First of all, it's explanation of your API. The second one is actually how you control this API. So first is specification, second one, the business logic. And fifth one is just you can run your code and your modified code inside Kubernetes cluster, but from your own laptop. So right now we have everything to start building and introducing logic to our operator, and actually let's do that. This is result of second command, and it will generate for you specification. As you see, the specification consists by 3 parts. This is select, insert, free groups, and storage. Each of them represent the own types of the own subset of the services. This is specification. Then you have your entire structure for the whole object. It consists of 4 basic components: its type, object, specification, and status. So type of object are pretty the same for every resources. Specification is how you define your application. Status, useful information for how your application behave, and you can store the your business logic information. Right now, I'm going to store in status actually storage status. That's right now it uses only 2 of them. First of all is operational, when everything okay, and expanding. Expanding status means that right now user adds 1 new node, and we should follow the procedure which is described before. So we should wait for new storage node or new storage nodes. After that, we need to update specification of every select pod, and after that we need to perform updates of insert nodes. And on the right part of the slide, you can see how VM storage structure looks. This is basic representation of YAML file which I showed to you. And here you just need to define the actual parameters from the YAML specification to the real types in Go. Good news here that some of the types are predefined, like not selectors, toleration, and some just can be mapped to sync, like label annotations. And you can reuse a lot of code from operators decay, but it will generate a lot of code by this spec. Optional field means that this field is optional, so just annotation. Next slide, it's actually the first, let me mention, this is the first part. As I mentioned, there are 2 types. This is API and how you describe your application, and second one is the controller and control part. Right here you see the result of command of generation controller. Controller will generate your VM cluster controller component, and the information which we're looking here is watch section. Watch section you tells for Kubernetes cluster about what you're looking for and what you're curious, and what updates it should send to you. And right now you're curious if something in change in kind of VM cluster, please notify me. VM cluster produces deployments and stateful set. So stateful set is used for storage component. Deployment is used for VM select and insert. One stateful to 2 stateless. So it's easy to use predefined components, and actually you can just create the pods, but you have pretty good orchestration inside deployment and status sets, so why don't use it just? And in watch definition for deployment and for stateful set, you define that you care about only 4 deployments and status set, which is created by your domain definition. So if VM cluster creates deployment and stateful set, and user change specification of this deployment, please inform and send event. If user change some another one, deployments, we just don't care about that. And that is specified by owner type. If you remember, I mentioned about owner section. So owner for deployment and cluster will be VM cluster kind. And in that case, all notification about these types will be received by this controller. And if we delete VM cluster definition, all downstreams, deployments, stateful sets, services, and pods will be deleted automatically. It's like you delete the resource of Kubernetes and everything delete automatically. Another one part is reconciled loop. It's where your business logic is in scope of operator SDK. And here we're curious about these pink lines. First of all, you define your specification and you try to get the specification by Kubernetes API from the Kubernetes. And basically it says, hey Kubernetes, please give me information about my resource VM cluster in this particular namespace and fill the structure. And in the end of that you will get full specification. What this specification is in YAML file, and it will be represented by your spec information in your type. And the second line is reconcile storage loop. It's where we handle logic, actually, where logic are, and I'll present the next type. So logic, how we handling storage. First of all, we are still curious about these pink lines. And the main orchestration looks like, okay, please handle the status of the cluster. If something is created or updated, but no new appear, handle storage will return just operational state. And okay, if state was operational and it's still operation, nothing to change, no need to update the cluster, and we just go and say this iteration is over, and I'm just waiting for another one modification of my resources. Otherwise, if user introduce new node, status expanded will be returned, and if status was operational and becomes expanded, we're going to update our status inside the definition. And here we are going to say that I want to requeue my request, and Kubernetes, please call me again. Why we need that? Definitely we can block your execution of your cluster and wait until new pod is appear and waiting for the ready of the new storage pod. But as we don't want to handle this business logic and state on your shoulders, so let's give Kubernetes this option. So this left side of the screen is the right side. There we can go a bit deep to the handle storage. And actually, first of all, we create the stateful set definition for our storage, because storage is represented by stateful set. And after that, we just comparing the statuses. If the current status of the storage is expanding, we don't need to perform any action. We just need to wait until these actions are done and wait. If we and right now we just perform check. Okay, is our pods are ready? If yes, just continue to do our regular handling and handle updates or deletion. If no, just say Kubernetes about, okay, please do another one cycle. Next one is if changes only specification or just new stateful status appear, we have stateful set in specification from VM cluster. We ask Kubernetes about existing specification, existing stateful set. We compare, so if it's not found, we need to create the stateful set. If it's found that something may change, and we just need to perform the update. And here we also have business logic, which defines the update procedure when user increase the number of pods, and we just checking the number of replica in specification and the real number of replica in stateful set. If user add more node, we just return the status, and this is how we start our handling the logic. And what actually happens when user expand cluster from 2, for example, for 5 nodes? First of all, we go to the update section and see that, okay, number changes. That's why we need to return new status. And we return cluster is in expanding state and just do another one cycle. After some time after just some time, the new pod disappear and new pod is in ready state, but we need to stop two new pods, so we're still waiting. If in that moment we have performed the command could still get our VM cluster, and it will show to us in the definition in the YAML file that VM storage right now is in expanded state. After several amount of time, when everything ready and the state of state will contain 5 new pods with the storage representation, the stages will be changed to operational, the status in the YAML definition will still be operational, and all other actions will be performed, like refreshing of information, refreshing of specification in VM select, using the same mechanism, and refreshing the information in VM select, VM insert nodes. Actually, how we check the status? We're using Kubernetes API, and we say, okay, for these labels, because your status has own labels which you defined, please use these labels and find all pods for these labels. And we just run through these pods, check if these pods in running state, first of all, and we increase count. And second, if we check that amount of pods are equal to our desirable state, so replica count. And based on this information, we just return need to wait or we don't need to wait, and return if we have. So, and for the VM insert and for VM select, we use pretty the same mechanism. Only one thing that VM insert waits for VM select, and VM insert just perform its basic rollout update, and no one waits for when it's ready, except the end application, because end application needs to somehow to write data to the cluster. So right now, I just showed you how you can do own your custom logic of life cycle of your application inside Kubernetes cluster using Kubernetes specific mechanism like rollout update, waiting, creation of the pod. So we just describe the behave, and Kubernetes does this behave, so perform these actions for us. Useful links if you want to start your own operator. First is Get Your Started video and Get Your Started doc. The third one is just book from the Red Hat about how to build operator. You can find some deep information about what event can be observed, how actions you can perform. Operator SDK framework and repository. And the last one, actually, I haven't a chance to describe it. And this is KubeBuilder. KubeBuilder allows you to do complex validation of your schema and add complex rule of your validation and perform some logic. For example, if you specify URL, string as URL should be real URL, and possible resource should be existing by following this result. So thank you for your attention. And if someone has a question, feel free to ask me, and I will be actually. Could someone tell me about the next steps? Should I move to the Zoom chat? And
just 1 second.
Yeah. Okay.
Guys, don't be shy, and yeah, we have to do this. Thank you, Artem. Yeah, don't be shy and ask your questions here, or just join our Zoom.
Yeah, while no one is here with a question, I would like to ask one. Yeah, thank you, Artem, for such an informative talk with a lot of details. But as I seen from description of your resources, you was talking about VictoriaMetrics infrastructure, but I haven't heard what exactly about is VictoriaMetrics. Sorry. Could you please explain?
Yeah, sorry for that.
Maybe someone doesn't know.
Yeah, this is open source project. I contributed to it. So the basic idea, this is time series database where you can store your metrics and time series data. So all information from Prometheus, from Taurus, from all this stuff. So you can store inside VictoriaMetrics. And right now it's the most performant, most fast, most less resource consumption database. Actually, yeah, it's like if you want to use something fast than Prometheus, install VictoriaMetrics. If you have problems with Prometheus and Flux, Graphite, install VictoriaMetrics. If you want to something reliable, easy to operate, and all the stuff, just install and perform. You definitely like. Everything is written in Go, and I believe there are many useful components inside the repository, not only cluster, but some useful things for the monitoring side. But it just covers the monitoring ecosystem of your infrastructure.
Mm-hmm. Thank you. Okay. I have one more question, maybe. Yeah, if you don't mind. I also heard about some, competition between VictoriaMetrics. I mean, competition in performance and some different storage. I guess it's right from the Prometheus team, and I guess it's some competition about a place in an open source cloud foundation. I guess so. Have you heard about that? Can you say some words?
I just heard about that a little bit, but what I know from the last benchmark, which Alexander Volyalkin did, single node on a big instance can handle about 56 million data points per second for the writing. So in 1 second, you can write 56 millions of data, so 56 of timestamp and file data points, and that's pretty huge amount, and that will be hard for any other tools to do the same. The most close tools is ClickHouse, but ClickHouse is general purpose database for analytics, not for time series data, but all other things, they may have rich infrastructure, but they are not perform so well.
Mm-hmm. Okay, thank you.
Anyway, guys, you can see link to Zoom room, and you can talk with Artem directly in chat using different language probably, and talk more deeply about Kubernetes. Thank you, Artem, so much. And we are mostly ready to present you our next speaker. She's from Berlin. I know she knows a lot of programming languages. And let's say hello, Jessica.
Hi, hi everyone. Thanks for having me. Super exciting to be on a little virtual tour.
We're happy to see you here. And I know that Jessica will telling us about very interesting topic in Golang, which it's about garbage collector. Am I right?
You're right.
Okay. Let's wish you lucky and please start your presentation.
Yeah, thank you. Thanks for everyone for giving up some of your Friday evening to join today. So yes, as he said, I'm going to be talking about garbage collection. And this is like a collection of ideas that I've been playing around with because I started being involved in a project with GoBridge with the potential of writing a chapter around garbage collection. And while that project's on pause at the moment, I thought, well, I've spent all of time researching and looking into this. It'd be nice to kind of share that a little bit with the community. And yeah, hopefully also get some feedback from you all as well. So yeah, maybe just to start with what this talk is going to be about, or what I'm aiming to deliver with this. So I would like this to be aimed at all levels, so also beginner friendly, but also interesting, hopefully, for more intermediate Golang developers. So I'm going to start with like an overview of digging into like what is garbage collection anyway, what are the main mechanics, why do we even have garbage collection, and then dig a little more down to what is Go's approach to that and how the garbage collection in Go is working. Then I'd like to cover a little bit around the tooling, because Go offers us such awesome tooling for observing our programs, and garbage collection is not missed out in that. So I will have a look at like the tracing tooling that we have available, so we can like visualize what's going on in our program. And I'd like to leave you or like kind of wrap it up with some ideas around how we maybe can approach this as developers, and what we can do to maybe optimize or be more sympathetic to the hardware that our programs are running on, and maybe like see if we can reduce or optimize for garbage collection. So as I mentioned, this is a work in progress, and I'm very open to feedback, either here or through Twitter, or on the Gophers Slack. You can reach out to me. I definitely would like to like continue iterating on this and see it as a journey rather than a destination. So yeah, a little bit about me first. So my name's Jessica. I am very flattered by my introduction, Micah. I dabble in a couple of languages, that's true. But I predominantly am working in my day-to-day life in Go. I'm a backend software engineer at Ecosia, which is the search engine that plants trees, if you haven't come across us yet. You can find me almost everywhere as Sleepy Pioneer. And I'm actually, I think what's interesting is I'm actually a career changer. So I switched into programming from an initial career as a camera assistant in film and television, and then a secondary career as a coffee roaster. So a little bit of a interesting background there, and I'm what I would call a self/community taught developer. So outside of work, you'll find me probably at a lot of meetups, normally in person, but now remotely. And I really am thankful to the community and for these kind of opportunities to be able to have that growth. So let's get into it. What is garbage collection and why would we need this anyway? Well, hopefully it's not going to be surprising to anybody that memory is not endless, and at some point we may have to think about releasing it. So typically our pattern when we're writing code is going to be to assign a value in memory, and then we will be able to reference it at a later point. And like Go is certainly no different to that. It's a common practice in most of the languages that we're programming with. And yeah, I think it's like this is the talk for you if you start thinking like, well, actually, what happens to that later? And I think this is the interesting entry point of garbage collection, of thinking about memory management, where our variables are living, and then also what effect they're long-term going to have on the programs that we write. So where do allegations go? Well, we kind of have these two concepts of like the heap and the stack. And I think when we are thinking about memory management, this is like predominantly where people start, of understanding that a stack is going to be data that's only going to persist for the lifetime of the function it's running in, or that constructs it. And it kind of gets reclaimed pretty quickly. Whereas the heap is an area where we can more long-term keep data after the function that's constructed it, at least, and like somewhere down the line, this is the kind of memory that we need to think about cleaning up. So if we didn't clean up the memory, what would happen? Well, there we're going to probably hit problems running out of memory, which means that our programs are probably going to start crashing. So at some point, this is something that for sure your program is going to have to think about, unless it's incredibly short-lived. And I think understanding where your memory goes is the first point of this. So luckily, we can actually use escape analysis in Go to have a look to see where things are being stored. And this gives us great insight to kind of start peeking into where garbage collection is going to be necessary, and what kind of values are being stored where. And I think the second part of that question is, well, do I need to care about this? Like, do I need to know where a variable's stored? Well, Go docs actually says you don't really need to know, because we have this compiler in Go that's doing a lot of the lifting for us, and it kind of is trying to make smart decisions about what kind of values are going to be persistent and what needs to go into what kind of storage. But I think it's kind of one of those things that if you're like starting out, maybe you not have to be concerned. But then as you get more curious about the code that you're writing and the program that it's running, I think that's the point where you start to go, well, actually, I'd quite like to know, even if I don't have to. At least that's my kind of approach to things. So we're going to accept now that allocations happen, and that we have them on the heap, and that if we don't think about cleaning them up, our program is potentially going to crash or run out of memory, and we're going to hit problems. So accepting this to be a truth, we could either start thinking about manually having to write something that would remove these values, and you can imagine what kind of algorithm you're going to need there, something that will look to see what values there are, what values are in use, what values maybe we still need. Or we could have maybe a built-in operation to check all those values and clean them up when they're no longer needed. So a garbage collector. And I think it's, at this point, with where programming is going, it's probably pretty necessary to have in a modern language, and to be able to, especially the way that Go is structured, it's very value-driven, very much about passing information around. It's really important to have this as a consideration. So let's get into Go's garbage collector. Well, I think, yeah, hopefully it's clear that like this was made in addition, like very early on, because they saw that this need was there. And also, I think one of the important things to think about is where are the programs running? So Go programs predominantly are kind of aimed or looking towards running on cloud software. And I think you have to think about it in terms of like, well, if we're adding extra resources, it's going to cost us money. And if they're resources that we actually no longer need, then that's money that we're just throwing away. So even though I think we live in an age where resources can seem kind of abundant, Like our hardware is still pretty much up to scratch with the kind of software that we're writing, although of course there's edge cases, depends what device you're programming for. I think in terms of cloud, it's equaling dollars, and I think that's why it's kind of important to have. The other thing with Go's garbage collector is they made a very conscious decision to go down the route of concurrency, which those of you that work with Go a lot already know. Concurrency is a big part of the language, and thinking about how to be able to write things in a concurrent manner is really kind of like at the heart of many of the starting points for Go. But that adds a lot of complexity. So like every Go routine has its own stack, and this means that being able to successfully manage this manually could be incredibly difficult. The last point here is the latency. So I'm going to touch a little bit on some of the different steps of garbage collection, but for the Go team, it was very important for them to ensure that while with this concurrency, that also was able to achieve low latency. And this would regard to the minimum amount of time that a program is paused for garbage collection to take place. So this was kind of the mission statement that Go put out for Go 1.5 in 2015, where they made some of the bigger changes for the garbage collector. And they kind of said, look, we're not doing this just to make a garbage collector for day. We're looking into the future of like where our programs are going to run and what's going to be important to Go developers in 2025. Well, we're halfway there. So I think it's a good point to reflect a little bit on what's being done. So as I mentioned, it's a concurrent garbage collector in Go, and it actually uses an algorithm that's fairly old. It's from the 1970s, and they've chosen to go down this route. Really, I think from my reading or my understanding, if at least, to kind of keep things simple. And I like that in Go, that a lot of it is very opinionated, and there's very clear ways to go down certain paths. And I think this also makes the language great if you're new in programming or if you're new in Go, because you get some really great consistent examples when you start to look into how to implement things. So yeah, moving on, let's have a look at how garbage collection is actually happening. So I split it up into three parts here for us to dissect, the first of which is the pacer. So this is running in the background, and this pacer is part of the scheduler. It's going to determine the length of collection and when collection is going to happen. And its main job is to make sure that garbage collection finishes before we run out of memory. So hopefully that makes sense to everyone. If we ran out of memory, the program may have crashed, and then we don't really care if garbage collection would happen or not. So it really needs to make sure it happens just at the point when the memory is full, or maybe just before, to have some wiggle room. The next phase is the marking. So Go is using what they call a tricolor marking system, where it's going through and inspecting values to see if they've been referenced from somewhere else. And if they have indeed been referenced, it's going to mark them as in use. At the end of that process, anything that has not been marked in use is free to be disposed of. It's not being referenced by anyone, so therefore it's fine for that to be cleaned up and swept away. So that's the last stage, the actual cleaning up of these unused values that through this marking process have been deemed as no longer needed. So, sorry, my slides seem to flicker a little bit when they're switching over. So when does the pacer even know? Like, how does it understand when our memory is going to run out, or when it should start the garbage collector? Well, like many things, it's going to rely on a feedback loop and information that it gets from the program itself. So the pacer, is going to have a look to see what memory is still in use after each collection, and on that, make a decision for when it will run the next collector. The next collection. It's also gonna, we have one dial in this, which I'll go over, like one control that we as developers can kind of like have an effect on. And for the next few slides, I'm just going to assume it's at its default, which is 100%. And this is the garbage collector percentage. And that's going to have an effect on this decision that the pacer makes of when shall I run my next collection. And that decision kind of looks a little bit like this. So if we could imagine the garbage collector runs for the first time, and after running, it determines that there is 2 megabytes in use memory. So these are values that are referenced elsewhere and that we absolutely need to keep. So if the garbage percentage is set to 100, which as I mentioned is the default, then the heap will be doubled, meaning we'll have 4 megabytes. Meaning that the pacer will say, I will run garbage collection next time just before or at the point where I hit 4 megabytes. And this is an ongoing loop. This is ongoing feedback. So if we imagine the next run of the garbage collector finishes with 5 megabytes, the pacer is then going to say, okay, now I'm going to assign another 5 megabytes to the heap, and the next collection will run it just before the 10 megabyte mark. Again, this is with the default setting for the garbage collector percentage set at 100. So let's switch gears and look at the marking phase that we discussed. And here is where it gets interesting, and we need to start thinking about when garbage collection runs, because this is where the potential latency is in this whole process. So the first step is going to be marking setup. And we have to turn the write barrier on for this, which means that there is going to be stop the world time. And this means we have to stop all of the application Go routines from running and pause them. And this is going to really depend on like what is running at that time to how much latency we have here. But ideally, it's going to be the minimum amount possible just to be able to turn the write barrier on before we can go into the concurrent section of garbage collection. And you'll see this turn up as sweep termination. Next stage is going to be inspecting and marking. And we're going to start with all the root objects that are on the stack pointing to variables in the heap. And we'll transverse along these memory pointers to mark all of the values that are in use. So you can imagine each one is branching off and pointing to different values. So we have to go through each possible step to see if indeed it is pointing to another value. Those are the values that we're marking in use. They are pointed to from somewhere else, and we still require those values to stay in memory. This is a part that runs concurrently, and depending on how much marking there is, will depend on how much of our CPU power is going to go towards this. But it does mean that application code can still run, like our program can still do things during this marking phase. The last step of that is going to be the mark termination. Again, this is going to be stop the world because we have to turn the write barrier off. And this is where that calculation for the next collection is going to happen. So what I just previously spoke about with the pacer deciding when the next collection will run. Let's drill down a little bit into this and look more closely at how this concurrent section of the inspection is happening. So in this example, and this is a very simplified example just to try and make clear what is going on here in terms of behavior, we have 4 Go routines. And at the start, they're all going to be running application work until we go into the first part of that stop the world time. Then they're all going to have to stop. And once and only once they've all stopped, we can turn the write barrier on. After it's on, we can stop our stop the world time, and we can start doing some of the marking. And initially, it's going to probably assign about 25% of the CPU. So in this example, 1 Go routine to do that marking work for us. The other 3, of course, can continue doing program work. However, there is times when just 1 Go routine is going to take too long for the marking. And in this case, the pacer is then going to enlist the support, let's say, of another Go routine and take up more CPU usage to be able to complete this marking as quick time period as possible. Of course, this is still concurrent. There's still 2 other Go routines, so we haven't had to stop our program running. But depending on this marking, we want to make sure that this marking phase is not lasting too long. So marking is finished. We need to turn off the write barrier, so we have to go back into stop the world, so stopping all Go routines. And after that, we can release them all back so they can do their program work. So the last phase of sweeping, what's actually kind of really interesting, I think, is actually going to happen when Go routines allocate new values to the heap. So I think that's great because that means that we do not have to assign that kind of latency to garbage collection. And in fact, it is going to be when we make a new allocation that we actually have to account for the sweeping to happen. However, that's only going to happen when and if we need more allocations. So I think this is a really smart approach for our GC. So next, I'd like to share with you a little bit of that in action, because if you're like me, seeing it in slides is great, but it's also kind of nicer to be able to look at that in code and kind of make it connect to the work that you're maybe doing on a daily basis. So what I've written here is an incredibly small program that essentially makes allocation here and prints out the length of this array of ints. I've also added in a repeat function so that will happen multiple times. And this is predominantly just to be able to then create a visualization of this, of it being allocated and then seeing where the allocation goes. So the first thing I will do is I will actually just run it without the tracer on at all. Just run the function as is. But what I am going to have on there is, and I just added these in, I'm going to add the garbage collection flags. So hopefully you can see this down in the bottom of my terminal. If not, I will share the repo with you. The repo is not really documented well enough to be an independent learning tool, but it will give you the opportunity to have a look at what I'm running now. And this GC flag is going to give us some information around what's going on in terms of allocations. And what we're looking for here is that determination of, are we actually putting values on the heap, or are we putting allocations over to the stack? And we can see clearly here that this Go tool is saying to us, yeah, here on this line 16, this value is escaping to the heap. And also, interestingly, on the line 17, the value that we passed through to the function print is also escaping to the heap. So here we can see from this evaluation that we are actually allocating 2 things to the heap. Well, that's kind of cool because I want to show you garbage collection in action. So, surprise, surprise, needs something on the heap to do so. All right, so let's have a little look further into that. I'm now going to run it with the tracing tool on. If you do check out this repo, you'll be able to see that I've added the tracer in a separate package. It is the bog standard example actually from the Go docs. So that's perfect because it does everything we need it to do. And I've just abstracted it away to keep this main file a little bit cleaner, but it's running the same program. Someone's saying, can I zoom in on the code? I will happily try and do that. Oh, that was potentially too much zooming in. The main thing here that we're going to look for will be the terminal. So do let me know if the output in the terminal, when I make the screen bigger, is not visible, because that's what I would predominantly like to demonstrate. Okay, and this time we are going to run this. I'm going to run it with the garbage collection trace on. I'm also going to limit it to run on one processor. This is process fed, sorry. This is only because I think it's a lot simpler when we look at the visualization to see what's going on. And again, I've got the flags for the garbage collector running. So what we get with this output, which I think is really interesting, is this line, or these lines here, sorry, that describe to us what's going on with the garbage collector. First of all, like how many times the garbage collector is running, but also information about the kind of goals that it had for cleaning up, and what was its starting point, and what did it end with. However, if you are like me, looking at lines like this can not be the most intuitive way of trying to understand what's going on. So Go gives us this rather awesome tool called the tracer, and we can open this up and then have a look at it in a more visual format. So let me just zoom in. Sorry, wrong tool. Here we go. Okay. So the first thing I'd like to point out here is that we can see this line about the heap, and we can see it's going up, and we can see it's going down. So that's good news. That means that we are adding allocations, and then assumably they're being cleaned up because they're disappearing, or they're no longer in use. We can also see here the different garbage collection work that's going on in our program. This is just an overview of like something is happening with garbage collection, but what we can actually zoom in is look at these kind of things where we see the mark assist is happening, or this one for this also mark assist, sorry. Let's see here, it shows you down below in this area that this is actually sweeping that's happening. So I think this kind of starts to give you a really good idea of like when your program is actually trying to run garbage collection, and it can help you to start debugging if you are having some issues with memory allocations, and also give you an opportunity to see how that actually takes place. So in the repo, I also shared a few examples of running it with different garbage collector percentages. Out of respect of time, I am not going to run those live now, but you can go to this repo, and I will certainly share the slides and this code in the chat and run them for yourself. And I think it's quite interesting to do so and see, as you turn that dial up and down, what is the effect on the amount of times garbage collection happens, and also when and for how long garbage collection is happening. So, sorry, 1 second. What I've maybe like came to realize from looking through this and trying to understand a little bit better what was going on is that actually a careful, or rather to my mind, an informed programmer can reduce the garbage collection overhead dramatically by using the language well. And this is actually a quote directly from Golang's FAQ. I think for me, the important part there is the informed. And I think having tools like we do in Go, such as the Go trace tool or the GC flags, gives us that insight into how the language is processing things that is essential for us to be able to gain understanding and make decisions around our programming choices. So how could we optimize for garbage collection? And how do we as developers have sympathy for where our programs are running? I'd like to present a few ideas. I think the first one is, well, we can certainly think about reducing the number of values on the heap. So being mindful of when we're allocating and understanding what allocations are going where. is, I think, the first step. So running these GC flags and looking to see, are your values escaping out onto the heap? And is that important? Is that necessary in your program? Is the first step that maybe you can take. Maybe also thinking about reducing the amount of allocated memory. So ensuring that if you do indeed have to allocate out to the heap or make allocations that escape to the heap, is it possible to make them smaller or take just a section? Is it really necessary to have such large allocations sent out? And lastly, maybe thinking about reducing the number of Go routines that are allocating. So earlier on, I spoke about how this is adding a lot of complexity for memory allocation, and that makes things more complex and more complicated. And if we can maybe make this a little less so, this is certainly going to be a little more friendly for our garbage collector and the pacer. So the future of Go's GC. If you're coming from another language, you may be familiar with other garbage collectors and other different algorithms for this. And is there any indication that Go is going to go off this path that it set for itself? Well, from reading, which was super interesting, reading through a lot of the proposals and the additions in Go, it certainly doesn't look like it. There are indications that we might get a few more dials. For instance, I've seen quite a few comments around set max heap, which hasn't made it into the language yet, but seems to be trialing. Also, something that was really interesting, actually, that I brought to my attention was that recently, I think you told me it was in Go 1.14, and I know you shared a link with me. They added it in the capability of the scheduler to be able to stop Go routines who were refusing to stop, which would be really important at this point where you need that first stop of the world and you need all the Go routines to stop. Up until then, it was possible that they would hang, and this would be like an edge case of garbage collection because it wouldn't be able to run at all. And that's something that they've kind of added that aids this whole process to be able to happen. So summing up, we've covered what is garbage collection, why we might need it, Go's specific garbage collector and why it's in the language, the different phases of garbage collection and how it interacts with Go routines. We've touched on stop the world time and latencies, with a few ideas on how to maybe optimize our code to be more sympathetic to the garbage collector. Definitely not covered everything on this topic, and it's super interesting. I have already been spending quite a few months working and researching on this. There's definitely edge cases that have not been mentioned. That is something that I would like to continue with, and maybe also looking at different possible algorithms for the Go garbage collector. I'd like to give a huge shout out to Daria, who collaborated on all the research included in this talk, to Bill Kennedy for being a massive inspiration and so supportive, and Rana, who is also speaking this evening, for her constant support. There's a couple of resources, as I mentioned. I'll share the slides so you'll be able to pull them out of there yourselves. This great topic, there's lots of information out there. This just scratches the surface for you to get started. Thanks so much for listening. And like I said, if you've got any questions, you can hit me up on Twitter, hit me in Gophers Slack, or shoot me an email. Thanks very much.
Thank you, Jessica. So I have one question, really. It's a very important question. Do you know typical mistake which people are doing with garbage collector?
A typical mistake that people do with the garbage collector. No, I mean, I think most of us just assume it's running and that it will do the work for us. I don't think that's probably not a mistake. I think it's fairly safe assumption. It very much depends on your program. Had an interesting discussion the other day about turning the garbage collector off completely, which is also possible with this Go GC flag. I think there's, again, I don't think it's really a mistake. I think there's reasons that you may argue to do it, but on the whole, it's probably not advisable.
Okay. So, and thank you.
Thank you, everyone.
Yeah, maybe we have some others, but yeah, I have one question too. Yeah, just
Okay.
recently, like no long time ago, I noticed the issue that was in a GitHub and it's still open. It was about that when you delete a key from the map in a Golang, it doesn't release memory completely, and it's directly related to the garbage collector. So yeah, I just would like to ask whether you know some details about that issue, because that's not very intuitive when you delete something and memory is not released.
Yeah, that's super. I have no idea, first and foremost, but it sounds super interesting. So if you could link me, I'd like to look into that as part of the continuation of my research here. But yeah, I mean, I think that's for me, the takeaway should be, let's observe more and let's look more at how our programs are running. Because I think with Go, at least my experience so far has been like we get so much out the box that it's kind of easy to just not think about these things. And that's why I thought it's really interesting if you do run tracing and you do run these various flags that you have to see where your memory is going, and delve deeper into that. It can, I think, in my opinion, make you a better programmer.
Thank you.
And it looks like we have a question, but Vladimir, could you please enable your camera? Yeah, sure.
Can you hear me?
Yeah, well.
Oh yeah, thank you for a nice presentation. It was really great and useful. One more question, probably it's not only for Golang, but actually about algorithm of mark and sweep. There are issues inside with memory fragmentation. How does Golang manage these issues with fragmentation? Because yeah, you understand that we have a small amount of memory, but we can't use it. And what is the plans? Do you know something? How to manage this?
Great question.
Thanks.
Yeah, great question. I don't know if I have an answer for you. I'm also not 100% sure if I fully understood exactly what you're specifically getting at. I know that I've read around different approaches for garbage collection that would give you these fragmentation issues, but I'm not 100% aware if that is a problem in the current implementation of Go's algorithm. Maybe you actually know more than me on this topic.
Actually, I don't know. That's why I asked. I know that in other languages like Ruby and so on, they have issues with fragmentation of memory, because the first algorithm was mark and sweep, and I guess after 2.5 version of Ruby, or probably 2.6 even, they improved garbage collection and created a stage to compact this memory. So we won't have any fragmentation, so a small amount of it would be like memory is compacted, so we can more efficiency to use this memory. And I don't know, is this issues existing in Golang world in a Golang actually or not? Because it's.
I mean, I know they have experimented with generational garbage collection as maybe like a continuation of the current implementation, but I think I don't know. From what I read, from what is open online for you to access, is that hadn't really been successful so far, and that they would continue with how they have it at the moment. They didn't see the absolute need for this. But yeah, I don't know. I think it'd be very interesting to do more comparison. I do not know Ruby at all, so other than like one.
You should try.
I think.
So
okay.
It's really interesting topic. I suggest you to join our Zoom room, and we can talk about it in Zoom really. Thank you so much, and
Thanks.
we are mostly ready for next speaker. As I mentioned, it's our surprise who Let me make short introduction. Hello, Rana.
Hi.
Could you please tell us what you're doing as Go and developer expert for Go? Because I really not sure understand what does it mean.
That's a very, very good question. Oh my God, so sorry, left the door open and the cat will interrupt this. 1 second.
Okay, no worries. Most of
As I heard, Google developer experts, they should help people, for example, in Stack Overflow or do some meetings or something like that. All right.
Yeah. So essentially, it's a program for people who are not employed for Google, so are therefore not biased in any way, who can represent the community to Google for Google technologies and vice versa. So help out with integrating Google products to the community. And
wow.
I'm a Google developer expert for Go, so that's what I do for Go.
Wow, it sounds amazing.
It's, yeah. No complaints, yeah.
What happens in Google during lockdown? Are you working from home?
I am not a Google employee, so this is the whole point of this. I am actually looking for work, so anybody who is looking at this can hit me up. I know Go. I've been working with Go for the past 6 years, so it's been an adventure. Yeah.
Okay, I wish you lucky, and let's start your presentation.
Okay, perfect. So, I was afraid of this, but I was also afraid. So, I'm sorry for the infinite loop in your background right now. I am going to turn off the camera because I am based in Berlin and I do not want to mess with the gods of the internet here. So I am so sorry, but yeah, you will be hearing my voice, so I will be here. So I'm just going to stop the camera now. Igor, are they seeing my my screen? Can you please confirm, because I cannot look.
Yep, it works.
Okay, perfectly. So let's begin. So the topic of the day is semaphores, and I have to say that it's a topic that is close to my heart, as is concurrency in Go, because the first projects that I wrote were the first code that I ever wrote in Go was actually highly concurrent, and has been the backend that served me for the first 2 years of me working with Go. So I was actually working with a lot of concurrency. I ran into a lot of issues. When I started out, I was actually working with Go 1.3, so many things have changed, and I've watched them change over time, and there are certain problems that I haven't been able to necessarily find the best solution for. But every time that I come up with a topic like that, I try to share it in a meetup. So here's one.
Rana, sorry for interrupting. Could you
Yes.
please make your presentation full screen?
It's not full screen because it looks full screen here. What are you seeing?
Whole window.
Any change right now?
Unfortunately, no.
No?
No. Are you sharing correct display?
Well, the problem is that I cannot see the StreamYard. Wait, sorry?
No worries. Right now, on your screen, I can see me and just whole window of Chrome.
And Chrome?
Yeah.
You mean Firefox? Okay, yeah.
Firefox, okay.
And now?
Yep.
You see the presentation now or not?
I see presentation, but it's not full screen yet.
Okay, I see what you're saying, because I was able to go back and forth real quick to be able to see what you're seeing. So I'm just going to stop the screen, and then I'm going to share again. My guess is that this might work better. This
Awesome.
better?
Yeah.
Yeah.
Oh, I
Everything is fine. Thank you.
Yep.
All right. So semaphores. We're going to dive into semaphores and what they are and what we want to use them for, and how we might be able to do that correctly. And I call this seriously how, because it's been it's been a journey, and you will see why. So let's talk a little bit about what it means to run things simultaneously or at the same time. So we have two concepts to discuss. One is parallelism. That is not what's on your screen right now. And the other one is concurrency. And concurrency is essentially running multiple tasks at overlapping times. Parallel or not, that depends on the machine or the resources that you have. This espresso machine supports making 2 cups of espresso, not only concurrently, but at the same time. That's parallelism. So this is concurrency. And I'm really hoping that you will be able to see this video. Oh, I'm sorry. Okay. I guess since it's a video for babies, we have a baby on an ad. So we're watching here a woman trying to dress up for babies while also keeping them on the bed and try stopping them from falling. That's a concurrent execution of multiple tasks, basically. So you can see that every time she has to break to do something else. This is what a person who is trying to multitask looks like, and this is what multitasking in a computer, this is how it works as well. So I'm going to let you enjoy this for just a little bit longer, because it is funny. By the way, it ends with her succeeding, and no baby is injured. So it's kind of has a good ending. So
I'm again sorry for interrupting you. I saw this movie, but looks like we are still see the first slide. The philosophy of running things at the same time.
You're not looking at the. You're not seeing the slides correctly. Oh, I see.
We are not
I
looking to the video.
Yeah, I see what you're saying. Okay. What is it that I can, there's something, okay, so this particular presentation is cursed. It is not you, it's this presentation. It's just cursed. And the first time that I actually held it, we didn't have this lovely YouTube video. Let me share, wait, my screen again. But first, I'm going to present this, all right. Are we happy now? We should be, right?
Yeah.
Okay.
Yes.
So this is our little fun video. This is what I meant. Well, I'm starting to think that it sounds a little bit crazy when a speaker talks about a woman dressing up babies without having actually being able to actually see the videos right now. So this is kind of a funny story for the ages. Well, hopefully you can see this. You can see that every time she's trying to dress them up. Hopefully you can see that, and that it streams properly. And every time she tries to dress another baby, something happens. She has to break up, to break from what she's doing, to break off to do something else. Let's say return a baby to bed, and so on and so forth. And it's a lot of work. What I want you to take away from this is actually one thing, that it is possible that running those tasks simultaneously, because of how many times she has to break off everything that she's doing, it is possible that it would actually take longer to do it like this. It would actually be easier if it were consecutive. So let's move on. I'm sorry, that's not what I'm doing here. In Go, we talk about, before, so context switches. So what she's doing, what she was doing, running around after her kids and trying to dress them while trying to keep them safe, is what we call in our world, in the real world, and also in computers.
Rana, I'm so sorry. I have
You're
to
so
interrupt you one more time. People saying that we are looking to static picture.
I see it again. I don't understand why it won't share the screen properly. I'm just not going to touch the screen again. So I'm just not going to try and change and fix the resolution or anything. Wait. So right now you're seeing context switches. This is fine. The video was not playing. That's not so good.
Yeah, let's try to see the video. Oh, it works.
Okay. So this is the video. Third time's a charm, Eagle. Hopefully you're enjoying this. Let's see what you're saying in the
it looks like my life.
I see it. Okay, Jessica approves. Thank you, Jessica. Well, this is not the right way to dress for babies. Now, as I never tried to do it, I know that I probably have no idea what the right way is, but since I do have some idea about how multitasking works, I can tell that it is that it is the wrong way to do this. Just observing as a let's call it computer scientist. So somebody with that kind of background, engineering background. I want you to observe here that what I really want you to observe and what I want you to take away from this is essentially the fact that had she had just dressed them consecutively without trying to dress them up while being on the bed at the same time and having to context switch between them constantly, it might actually take less time to do this. I'm saying this because it is actually essentially what's happening in your computer all the time. So let's move on from this video. I'm just going to make sure now that you're seeing what I'm seeing. Perfect. So this is essentially context switches. Context switches are kind of evil. Jumping around, jumping like the woman between tasks is what context switch is. And it can actually make the tasks that you're trying to perform, just trying to perform them concurrently makes them run slower. So in Go, we talk about concurrency, just so we're clear. We don't actually talk about parallelism. The fact that we don't talk about parallelism does not mean that things will not run in parallel. They might run in parallel. So let's talk about threads a little bit. From Wikipedia, threads are a way for a program to divide or split itself into two or more simultaneously or pseudo-simultaneously running tasks. There's nothing much more to add. It's basically how we execute tasks concurrently. In Go, we don't use threads directly, but we use Go routines instead. Sorry, I thought I lost you for a second. Go routines are lightweight threads where a Go routine can run on one or more threads. They are lightweight threads, which means they can start on one thread and then be taken off of it by the Go scheduler, and then resume on another thread instead. Who is managing this entire thing? It's the Go scheduler, and it is trying to reuse threads and minimize context switches for us. But we have to make sure that it's kind of successful. And you can see here how we can start a Go routine. So in this case, we're starting a Go routine with an anonymous function that takes an integer and prints it. And this code will run concurrently. And now we have channels. So channels are message queues of any type that can be used safely to communicate between Go routines. And channels have capacity that's very important when we are talking about semaphores. We can abuse that a little bit. So what do I mean by capacity? When we create a channel, if we give it a number, that we can make it without giving it a number, and then will be an unbuffered channel, which means that it has no buffer, or a buffer of size 0, essentially. And a buffered channel has a capacity. In here, I'm making a channel of size 3. And I'm writing 3 messages to the channel, and the channel has a capacity of 3, so that means that it can hold 3 messages, or 3 integers in this particular case. And when I try to write the 4th into it, I block forever in this particular case, because that's a bug. In order for this not to be a bug, there has to be another Go routine running that will read from this channel. So once it reads one message out, then I can write my one message in. Now, the rule is first in, first out. Let me check the chat and that everybody's on board. Everything is fine. Nobody's complaining. Nobody's complaining, right? Good. Then channels empty work essentially the same thing as when the channel is at capacity. We make a channel with capacity 3, and then we write 3 messages into the channel. Then we read those messages. This is how we read them. When we have read the 3rd one, it's empty. And now if we are trying to read from the channel again, we block forever the same way. The only way for this Go routine not to be forever blocked or forever deadlocked would be if another Go routine writes to this channel, and therefore we will have one message to read from it. And this is how this works. We're going to use this. So introducing semaphores. Semaphores are a solution that is introduced into a concurrent app when things get more complicated. What do I mean by that? Okay. They're a way to limit access to a finite resource, but okay. So I mean, it's good enough. So they're a way to limit access to a finite resource, and I'm going to give you some examples here. So these are finite resources, bandwidth, for instance. like if we're trying to download 1,000 videos at once, it can result in each video taking way longer to download because we have a certain bandwidth. Not only that, there could be a penalty for trying to open that many connections to a certain service. So there's a lot of problem there, and we could be throttled. So we could be actually penalized for trying to do that. File descriptors, there's a finite number, and we cannot exceed it. If we do, we will crash, or we might crash. Trying to perform too many operators at once on a database can overload it and make it work way more slowly. And we know this from anything that is overloaded. Could be even your computer when you're trying to run too many applications that consume too much CPU, for instance. So sometimes adding concurrency makes things go slower, and we need to be able to limit the amount of Go routines that we start to handle different tasks to prevent things from getting slower and maybe even crash. So this brings us to what semaphore is. A semaphore is the way that we do this, the way that we achieve, the way that we limit to usually a predetermined number, the number of Go routines that we're going to allocate a certain task. And a common technique, and this one is from Effective Go, is this, and it uses the capacity of a channel and to maintain the number of Go routines that are going to perform, in our case, the action process right here. So we make a channel of integers in this case of capacity max outstanding. That's, I'm guessing, the number of outstanding messages that we will process. We enter a function handle. We write. You can actually do this vice versa. You can actually read to a channel and write for it, or write into a channel and read from it at the end. Like you can. This is interchangeable. You can use either technique to handle a semaphore. In this case, we are writing to the channel, and if we succeeded, then we know that the channel is not at capacity. That means that currently there is less than max outstanding Go routines that are accessing this, that are going to enter. We run process, and then we read from the channel. We know that we can read from the channel because we wrote the message. So we wrote the message. It means that we can read easily. And this is how this is done. So we cannot actually exceed the capacity. So we know that no more than max outstanding Go routines are going to be able to access process. Period. And this is just how it's done. Now this is nice. However, there is a problem here that this Go routine is going to Go routines that execute handle is clearly created outside of handle, because we don't see the Go command right here. We don't see it. So somebody called Go handle or something that calls handle, but in the context of a Go routine, and we can't see it. So that means that we are allocating, or we are accessing, is that multiple Go routines can get stuck. So let's say that max outstanding in 20. I have 100 Go routines that are calling handle. 80 of them are going to get stuck. And if process is taking a long time, then it could grow to, I don't know, 1,000, 2,000. I don't know how many, what kind of resources they're holding on. Our app could blow up. So what we are looking at here is basically like, let's look at this approach. So let's talk about the approach that we just saw. This is the first approach. Make the channel. In our case, I wrote here size 10. We acquire the semaphore, we run process, and then we release. And in this case, we have no control over how many Go routines are waiting. So let's say that 1,000 Go routines are trying to access this code, then 990 are waiting. In approach 2, we first acquire the semaphore, and then we start a Go routine that will concurrently call process. And when it is done, then it's going to release the semaphore, release its object. We have another option. So this is from Effective Go. There is also a package that a lot of people don't really look at, a repo called golang.org/x. It's for everything experimental and some old and obsolete stuff also for Go. And it offers a sync semaphore package that has never made it into the language. And I wanted to look at that one. And we are going to actually look at that one, and we're going to acquire the semaphore, and we're going to compare the two approaches. Approach 1, which is to acquire after starting a Go routine, and the second one before. And finally, why not just keep using semaphore? We can just spawn the amount of Go routines that we want to handle a certain task, create a channel of tasks to run, and let it read from the channel, and let all the Go routines read from the channel, whatever tasks they have, and we run them concurrently. So we are essentially reusing the same Go routines. So we're going to have Go routines probably living forever to run these tasks for us. Some obvious downside to this might be that if I only want or need I get 2 tasks, then I have maybe 20, maybe 100 Go routines that are waiting for some work to do and have nothing to do in the meantime. But that's kind of slim because of how Go works, so should be okay. But is this solution preferable? So we're going to look into all of these things. Now I'm going to leave this for a little bit open for a little while, so that to allow people to to browse there. So who's on board? Who's not on board? Okay. I'm going to share a different screen now. We're just going to move to the repo where it all happens, all the magic. So hopefully you're with me and you're at Sema presentation. And if you ran into some problems, you were not shy about it, and you said something. I am getting a private message. Okay, nothing is burning. I'm just going to proceed as if everything is fine. So, Sema presentation. I'm going to remind you that the first approach I'm hoping this is zoomed in enough. The first approach, the effective Go approach, was to first start the Go routine. Well, we assume, because we didn't see the instruction with the Go keyword to start the Go routine, so we just assume. So first we start the Go routine, and then we're going to acquire the semaphore, and then we're going to release it. Now this is how that's done. And the second approach is we are going to try and improve Sema1, or at least see what happens if we create the Go routine after acquiring the semaphore, which means that we will essentially reduce the number of Go routines that we have pending to 0. We're not going to have any pending Go routines. And we're going to see, so in one, we're going to have multiple Go routines waiting, but then they're going to be waiting, and so which one should be faster? How is the scheduler? So we saw how concurrency, how trying to assign a task, and how messy it is to try to assign a task in our case, we're going to have to start a new Go routine, or maybe, and we're going to have multiple threads. So there's a lot going on here. I was actually curious to see what will happen now. I'm going to go to the code, just show you the code for just a little bit tiny. So we have Sema1 and Sema2. This is the repository here. Sema1, Sema2, Sema3, and Semaphore. And there is a request. The function to handle request actually increases the count. So I just wanted to make sure, and I wanted to show that there are no bugs in this code, and we actually process the same amount of messages as we receive. And the second thing that we do is we are calling Fibonacci here. This Fibonacci is a recursive Fibonacci and therefore costs a lot. Well, it is essentially my way of calling a function that will be kind of slow, but still not use sleeping or any kind of anything that will give a break to the CPU, essentially, because I want to test how things truly work. Let's call it, like, I want to simulate something very, very specific. Now, Sema1 and Sema2 are essentially the same. They're essentially the same. The only difference is where we acquire the semaphore. So in Sema2, this line will be moved here before the Go instruction. And this is it. This is the whole difference. And we're going to benchmark. Now, benchmarking is tricky because benchmark likes to send different numbers to the benchmark, so to allow you to test with changing numbers. In my case, I wanted to test 10 million messages with 10 with a growing number with 10 handlers. I didn't want to start with 1, which is what usually benchmark starts with. So using BN made no sense. I didn't think I should. I wanted to do it with very, very specific numbers. So I wanted to see how hard or easy it will be to handle 10 million messages with 10 handlers, 100 or Go routines, 100 Go routines. So this is basically the size of the semaphore. How many handlers we're going to allow to call process. And this is it. So, and the way that you do that, if you can't just use the benchmark increasing numbers and you want to define your own, the way you do that is with this. So you define bench time, and you give it this little suffix here, this x. So just test me. Okay. So actually the numbers apparently that I decided last night that I was going to give you is 1 million messages and not 10 million messages. The reason is, by the way, Sema3 that just refuses to come back with 10 million. So it's kind of a problem. But bench time, if you can give bench time whatever you want, if you use seconds, milliseconds, etc., for MS for milliseconds, S for seconds, and it will test and it will benchmark your code over time, over the time that you gave it. I just wanted BN to be the number 1 million, and this is how I set it here. I am benchmark dash benchmark equals dot means that I'm going to run all the benchmarks in this package, in package sema1. This is it, and well, you invoke it using go test, and you give it the name of the package, and voila, you get results. So something to be said here, the operation here is essentially what the operation here is actually a little bit counterintuitive, because usually you benchmark a set of code, but this is not how it works with benchmark with a changing number of n. So by setting the number to 1 million, I'm essentially saying here that it took to run with 10 handlers to run 1 million. It took 547 nanosecond per operation. The operation is actually a message here. So it's not a good number, by the way, and I've never been able to increase that number significantly. I'm just going to say this in advance. However, you do see that there is a significant decrease as long as we are allocating more handlers, and then there is an increase again at some point when we have, and it will be easier to see this maybe with playing with a little bit of different numbers, with a different number of messages. You can actually see different things here. I'm hoping that everything is good so far. I'm just going to make sure that nobody is writing me any messages and that you didn't lose me. Okay, so it looks okay, so we proceed. So we can see here something like a parable sort of feeling, or a gut feeling, that the more Go routines you have is actually not so great. So there's like a good middle where you have an optimal relationship between the number of Go routines that you want, or the size of the semaphore, or the weight of the semaphore, and the number of messages. So then we have sema2, and sema2 actually looks a tiny bit better. We do see that it takes longer to process a message with fewer handlers, but it actually looks pretty more or less more constant over time. So it looks a bit okay. I remind you that this is the situation where we have where we don't create a Go routine before we acquire the semaphore. So we don't have anything waiting, but that also means that we don't have anything ready to execute right now. Like whenever we want, there's already a next Go routine that is waiting to execute. So whether the scheduler is handling these things well, not so clear. Then sema3 and semaphore are exactly the same things, except with the Go semaphore package. I kind of lost my window. Okay, there it is. With the Go semaphore package, you can actually look at it. It's quite nice. So let's have a look. I'm hoping that I'm sharing this window. I am. This is great. What's interesting about this package is not what we're going to do with it, actually. What's interesting about this package is its interface. So we create a weighted. We are going to create a weighted semaphore, and then we can call acquire. You can see that we're giving acquire context, which means that we can actually cancel the acquisition if it waits a long time, which is kind of nice. And then, by the way, you can actually do that also with the semaphore that we had. You just need to, instead of instead of reading or writing to the channel, depending on how you decided to implement this. In our case, let's say write to the channel. So instead of waiting to write to the channel, you can run a select, let's say with a timeout or with a context context done. And then you can actually cancel trying to cancel the acquisition of the semaphore. What's really interesting is not this context, but this right here is that you can actually acquire more semaphores or more, I don't know what to call it, like the semaphore is the structure, but to acquire your lock, let's call it the lock, you can actually acquire more than one lock. And let's say that you know the weight, you can actually decide to maybe acquire all of them if there is a certain task that cannot run while other tasks are running. So there is actually interesting. There are actually interesting things here. The same goes to release. So, and there's of course the try acquire, which will just immediately leave if you cannot acquire the lock, which you could also do with select try to write and a default, and this will work the same way. So we want to basically do, well, the standard way. We're just acquiring one lock and then releasing one lock. So we're not doing anything more clever here. One we're going to do inside the Go routine, and the other one we're going to do outside of the Go routine, which means that we're going to control the number of Go routines that are running, same as 1 and 2. And these are possible results. Now, this is where things get interesting. You can see that this right here is horrifying. With a low number of Go routines, we actually can expect things to blow up with the with the nanosecond per operation. And if you want to see how bad it gets, try running this with a benchmark of not 1 million, but 3 or even 10. I think 3 is where things get really bad. If I remember correctly. And yeah, it's quite interesting why that is. And the reason is because the semaphore, the reason is probably, I actually never profiled it. Jessica, by the way, if you're interested, since you have great experience with a tracer. So it will be quite interesting to try and see what happens there. But what I'm assuming is happening there, this semaphore package is using mutex, and my guess is that 1 million Go routines are trying to obtain the lock for this mutex, and and therefore are failing, and only 10 will be allowed. So something about how we're testing this, and it's actually quite important. I should have gone into this a little bit more to begin with, is this. So the way, sorry, it's not here. It's in request. the way that we're doing all of this is with this function serve, which is actually not serving anything, but just what it does, it creates a slice of requests of the size of num messages, which is in our case 1 million. And you will notice that this is a slice, so it's not a channel of requests coming in or anything. It's just a slice. And the point is to essentially start the testing with 1 million messages, or with mimicking 1 million messages already waiting for you. And this happens a lot in backends when you start a service that was down for a while. It has a lot of backlog to pick up. So this is my way of trying to create a real bottleneck, something that is so depressing, the kind of thing that will make an engineer spend hours trying to troubleshoot in production, trying to do this before we get there. So we can see that when this kind of bottleneck, this package doesn't actually work very well. However, this package does support really interesting things like obtaining multiple locks, etc. And honestly, it works incredibly well with the other approach. So when you limit the number of coroutines that are trying to acquire a lock, it works perfectly well. I think it gives us better performance than everything else so far, and that's kind of awesome. So kudos to the Go team for an awesome package. And then we have the workers approach. The workers approach is essentially, why do we need a semaphore at all? Why do I need to start spawning Go routines when I get a request? I can just define a set of requests, and sorry, I can just define a set of and spawn a set of Go routines and have them pick up requests as they go. I did something here, like you have to make a certain choice here. Is obviously if you want to have Go routines or a set of workers that are constantly running, constantly just running. If you do that, you're going to have to define what the size of the channel of the requests that they're handling is going to be. Obviously, an unbuffered channel means that you will be writing the requests very, very slowly to it, and therefore they will be reading it slowly. So this is something that, this is a number that you will play with depending on what your app is doing. And now that we defined a channel with a certain capacity for the number of requests that are coming in, and I'm going to feed it here. Let's go. Let's have a look at the entire code, shall we? So we received the slice of requests that we have. We created a channel for them, and now we are going to sorry, it's here. So here we spawned the number of Go routines that we wanted to have. That's max handler. That changes 10, 100, 1000, etc. So we spawn all of our Go routines, and our Go routines are going to read from that channel until it closes. They're going to read all the requests until and then they're done, and they report that they're done. So essentially, we're starting, unlike we're just spawning Go routines here. And here we are writing the requests from the request slice into the incoming channel where the handlers are going to read them from. So this is essentially it. It's the same thing as here. And this is interesting. This is interesting because it works differently, completely differently what is happening here essentially is that you're going to see this number climbing the more Go routines you have. And why? Because we're driving the scheduler insane. So in this particular case, we're having 1 million messages, and we're trying to distribute them between 1 million Go routines. So that's kind of crazy, right? But this is what's happening here. It's not happy about it, and therefore we're seeing a decrease. So what's the conclusion from all of this? And again, like, this is homework, you know, I want you to profile it to see why. What's the conclusion from this is that you're going to get very, very different reactions, depending also on what your app is doing. So whatever approach you choose, you probably want to profile it to see what's happening. In some cases, by the way, in the original version of this talk, I actually wanted to get into how what your app does actually matters to that kind of semaphore that you're going to use. The reason is that it's actually similar to what Jessica showed you earlier. Depending on what your scheduler is doing or busy doing, depending on how your memory consumption is, depending on a lot of things, you might actually be able to utilize your CPUs more or not. If you profile, by the way, if you profile any of these solutions, you're going to see a lot of holes in your in what your cores are doing. You're going to see that they're not working at full capacity all the time. It doesn't look like an unhealthy app, but it doesn't look like an app that actually utilizes all of its resources the way that it's meant to. And I'll be honest, I have actually never managed to get there with any app that I wrote using any type of semaphore before. But that again, I wish you luck, and I'd be very, very interested in finding out. You have a suggestion for online code review? Deferred WG done. I don't know where we're talking, but thank you very much. Yeah, this code was written only for this, for the sake of this, of this presentation. So I hope that it's accurate enough. I don't think that there are any bugs because I ran it probably hundreds of times, but there might be small things like deferring wait group done. So thank you very much. Okay, so I think we're done with this. I'm hoping that you had a good time and you enjoyed yourself, and I'm hoping that Igor is going to just stop at any point and tell me.
I'm here. No worries. I'm here. So it's very, very interesting topic, and it's very difficult for people who just join Go language. I spent mostly a week to understand how this topic, why many Go routines doesn't work faster.
I have to say that with this, because something I don't know if I actually got into, so the Go scheduler is trying to do very sophisticated things for us, and one of them is trying to create essentially a thread pool for us, and minimize the costs of threading, of using threads at all. And I think they also changed it quite a few times. So for instance, things that I've heard at, like, I don't know, 1.4 or 1.5 are no longer relevant. And sometimes, like, I have to actually think in my head, like, oh, so this might now create, and by the way, with 1.14, I think also Jessica mentioned it quite wisely. There is preemption now. So a Go routine that goes rogue, like my Fibonacci there, that goes rogue and does not allow to release resources will be stopped. So I think we all need to profile our code a little bit to see that at the very least, like, things did not change dramatically since before. So yeah, thank you.
I guess Denise has several questions for you.
No, actually, I would like to thank you for such a deep technical analysis of such a great concept as semaphore. I would like to tell for those who are not familiar, in Go we have a great package which called Think, and an experimental package is also Think. There are many such concepts that you can get familiar with. Thank you for your talk. Yep.
I don't actually know if the semaphore in the sync experimental package was ever intended to enter the Go programming language that also has a sync package. I don't actually know. I've been wondering about that, but I haven't checked. There's probably documentation somewhere about this that I haven't found, and I don't know that it will enter. But yeah, it does exist, so you can play with this. And yeah, I always try to. I'll be honest. So I've been an engineer, you know, quite a long time now. I think either 16 or 17 years, and I actually made quite a name for myself while building something of a small cloud about 15 years ago. When people around me didn't even know what that was. And then it turned out that a lot of people were doing similar things all over the world, and then it became formalized into what we know today as the cloud, things like that. So it's kind of awesome. I'm sorry, apparently there's construction at 7:30. Sorry, that just happened. I don't know, no idea. Yeah, I believe in diving into crazy code and trying to I really truly believe in that, and this is actually what we do also at Women Who Go. We take difficult topics and we try to unravel them, and it works if you're trying to improve yourself. It really does work. I hope you enjoyed it, even if you're a beginner and you didn't understand everything. I hope that maybe you can take a few things away from this as well.
Okay, thank you so much.
Thank you.
So I think, guys, you can take your Friday's beer and join us in Zoom, and we can discuss this topic a little bit more deeper, talk about Go routines, semaphores, and other Gopher stuff. Thank you, and see you in another meetup. I hope it will be soon. See you, and bye.
Bye.